One day, farmers want to enclose a rectangular field. He is having a length L of the fencing material. He is facing the problem to enclose a rectangular field of the maximum area with one side bordering a river. A man was passing by him and asked his problem. After listening to his problem, he said, "You need to learn the concept of Maxima Minima." A farmer asked, "What is it?" "Let me explain to you out this. In the above case, the farmers need to examine the maximum or minimum values of the given functions. To assess such problems, we first formally introduce the maximum or minimum values of the function and points of local maxima and minima and the test for defining such points. Now, let's define what is maxima first. Let f be a function defined on an interval I. Then f is said to have a maximum value in the interval I if there exists a point C such that f of c should be greater than f of x for all x element of I. And the number f of c is called the maximum value of f in I. And the point C is called the point of maximum value of f in that particular interval. Mainly, maxima are of two types, local maxima and global maxima. Now we focus on what is minima. Let f be a function defined on an interval I. Then f is said to have a minimum value in I if there exists a point in C such that f of c should be less than f of x for all x element of I. Here is a representation, and as you can see, point C is the point of minima and f of c represents the minimum value of f at that point C. Like maxima, minima are also of two types, that is local minima and the other is global minima. And in case if f of c is neither a maximum value or nor minimum value of f in I, then the function f is said to have an extreme value if there exists a point C in I. In such cases, that point C is called extreme point. For example, f of x is equal to x element of 1, 2, 4. It means every monotonic function f in an interval I, the function is either increasing or decreasing in I. Now, let us discuss about continuous functions with multiple maxima and minima. As you can see from the graph, it is observed that the point A, B, C and D are called the turning points because the function changes its nature from decreasing to increasing and vice versa at these points. So, the point A and C are called local minima. They are the valley points. And the point B and D are called local maxima. Now, let us concentrate on this in detail. Now, the question is, what is local maxima? Let f be a real valued function and c be an interior point in the domain of f. Then the point C is called the point of local maxima if there is an h greater than 0 such that f of c is greater than or equal to f of x for all x in the interval c minus h to c plus h. And the value f of c is called the local maximum value of f. Now, at point x is equal to c, f dash of c is equal to 0, right? The first derivative is 0. And the function f is increasing, that is f dash of x is greater than 0 in the interval c minus h to c. And it is decreasing in the interval c to c plus h. So, as it is decreasing, f dash of x is less than 0, right? Now, what is local minima? let's see. Here, let's take a function f be a real valued function and c be an interior point in the domain of f. Then the point c is called the point of local minima, right? If there is an h greater than 0 such that f of c should be less than f of x for all x element of in the interval c minus h to c plus h. And what is this f of c called? F of c is called the minimum value of f, right? Now, if we look at the graph, at point x is equal to c, f dash of c is equal to 0. Here the function is increasing in the interval c to c plus h. So therefore, f dash of x is greater than 0 in this particular interval. And it is decreasing, that is f dash of x is less than 0 in the interval c minus h to c. Right? Now, we have to learn some important theorems related to maxima and minima. Let's see one example. If f of x is equal to x cube, what is f dash of x? Taking the derivative, we get it as 3x square. Now, f dash of 0, what will be the value? The answer will be 0. But 0 is neither a point of local maxima or a local minima. Therefore, this point is called the point of inflection, right? To understand this concept deeper, we need to know about what a critical point is. Now, let's see in detail what a critical point is. Maxima and minima exist at critical points, and these points contain stationary points. So, critical points are the points in the domain of the function f at which either f of x is equal to 0 or f dash of x does not exist. That is the point of discontinuity or it is not differentiable. With this, let us talk about the working rule or algorithm for finding the points of local maxima and local minima using first order derivatives. The following test applies only to continuous functions like polynomial function and trigonometric function. And at a critical point C in I, put y equal to f of x. Second step, find dy by dx or f dash of x. Third step, put f dash of x is equal to 0 and solve this equation to get the critical points or stationary value of x. Now step 4, consider x is equal to c, that is at the critical point. And if f dash of x switches a sign from positive to negative as it increases through c, then the function f of x has a local maxima at x is equal to c, as you can see the graph. Now, next step, at the critical point, if f of x switches a sign from negative to positive as x increases through c, then the function f of x attains a local minimum value at x is equal to c. Now, step 6, at a critical point, if f dash of x does not change its sign as x increases through c, then the function f of x is neither a point of local minima or local maxima at x is equal to c, and that point is called the point of inflection, right? Now, suppose we will be having this curve as our function and we need to examine each and every point of local maxima and local minima. Here, C1, C2, C3, C4 are the critical points and we require noticing the differences in the sign of f dash of x to determine the local maxima and local minima. Now, let us focus on the next, that is second order derivative test to find local maxima and minima. If the function f is twice differentiable at c, we mean the second order derivative of x exists at that particular point c. Now let us do how to perform the test to examine the local maxima or local minima using second order derivative. It is much easier to apply than the first order derivative. In the second order derivative test, Let f be a function defined on an interval I and c belongs to I. Let f be twice differentiable at c, then x is equal to c is a point of local maxima if f dash of c is equal to 0 and the second derivative, that is f2 dash of c, is less than 0. Then f of x has a local maxima at x is equal to c. Alright. Now, x is equal to c is a point of local minima if f dash of c is equal to 0 and f2 dash of c is greater than 0. Then f of x has a local minimum at x is equal to c. And the test fails if f dash of c is equal to 0 and f2 dash of c is equal to 0, then f of x represents the point of inflection at x is equal to c. Now, let's exemplify what we have studied. Locate the local maxima and local minima of the function f of x is equal to x cube minus 6x square plus 9x plus 15. And also, you need to locate the local maximum and local minimum values. Right? Let's see the solution. Here, first we have to find f dash of x, and given our f of x is x cube minus 6x square plus 9x plus 15. Now, taking the derivative, we get it as 3x square minus 12x plus 9. Right? Now, we need to substitute this equal to 0. So, 3 into x square minus 4x plus 3 is equal to 0. Again, we get x square minus 4x plus 3 is equal to 0. And this can be written as x square minus 3x minus x plus 3 is equal to 0. Now, which implies x minus 1 into x minus 3 is equal to 0. So, we get values of x as 1 and 3. Right? Now, next we need to find the second derivative. We know f dash of x is equal to 3 into x square minus 4x plus 3. So, taking the second derivative of this, we get 3 into 2x minus 4 plus 0, and this is equal to 6x minus 12. Now, we need to substitute x is equal to 1 in f2 dash of x. And what will be the value? F dash of 1 will be equal to minus 6. On substituting, we get it as minus 6. So, the value is less than 0. That is, the second derivative value is less than 0. So, what it represents? F of x is maximum at x is equal to 1. Why? Because at x is equal to 1, f2 dash of x switches from positive to negative. So, f of x has a local maximum value at x is equal to 1. Now, we need to find the local maximum value. We identify it as maximum at x is equal to 1. Now, we need to find the local maximum value. So, for that, put x is equal to 1 in your f of x, and you will get f of 1 is equal to 19, and this is the local maximum value at x is equal to 1. Now, to find the local minimum value, we need to substitute x is equal to 3 in f2 dash of x. So, substituting, we get f2 dash of x is equal to 6, whose value is greater than 0. So, since f2 dash of x is greater than 0, f of x is minimum at x is equal to 3, because it switches from negative to positive, and f of x has a local minimum value at x is equal to 3. Now, we need to find what the local minimum value. For that, put x is equal to 3 in your f of x, and you get the minimum value f of x is equal to 15. So, on solving, we get the result as 15. So, the minimum value, we get it as 15 at x is equal to 3. Right? Now, let us concentrate on the maximum and minimum value of a closed interval. Now, let us consider function f given by f of x is equal to x plus 2 in the interval 0 to 1. The function is continuous and neither has a local maximum and minimum value. Now, if we extend the domain to a closed interval 0 to 1, now at x is equal to 1, f of x is equal to x plus 2, substituting the value 1, we get it as 3. Now, at x is equal to 0, what is the value of f of x? F of x is equal to 0 plus 2 equal to 2. Thus, the function has maximum value 3 at x is equal to 1, and it is called the absolute maximum value, or it can be called as global maximum, or it is the greatest value. Similarly, the function has minimum value 2 at where? At x is equal to 0, and it is called absolute minimum value or global minimum, or it's the least value. Let's see through the graph. Here, the graph shows a continuous function defined on a closed interval a to d. Now, the absolute maximum value, where will be the absolute maximum value? At a, that is, the value will be f of a. Now, what will be the absolute minimum value? Absolute minimum value is at point D, as you can see here, and the value will be f of D, right? So, it has a local maxima at point A and C. So, corresponding maximum value at these points are f of A and f of C. Now, it has local minimum value at point where B and D, the valley points. And what are the minimum value? Minimum value will be f of B and f of D, right? Now, let us look on theorems based on this. Let f be a continuous function on the interval I, a to b, then f has the absolute maximum value and f attains it at least once in I. Also, f has the absolute minimum value and attains it at least once in the interval I. Now, let's see the next theorem. Let f be a differentiable function on a closed interval I, and let c be any interior point on I, then f dash of c is equal to 0 if it attains its absolute maximum value at c, and f dash of c is equal to 0 if it attains absolute minimum value at the point C. With this result, let us discuss on a working rule for finding the absolute maximum and absolute minimum values of a function in a closed interval. So, the very first step is we have to evaluate all the critical points of f in the interval a to b. Remember, it's a closed interval. Second, evaluate f at all the critical points and at the end points, that is a and b. Third one, the highest value will give you the absolute maximum f on the closed interval a to b, and the lowest value achieved is the absolute minimum of f on the closed interval a to b. Now, let's see one problem. Find the absolute maximum and minimum values of a function f given by f of x is equal to 2x cubed minus 15x square plus 36x plus 1 on the interval 1 to 5. Let's see the solution. Here, given f of x is equal to 2x cubed minus 15x square plus 36x plus 1. First, what we have to do? We have to find the critical point. So, for that, find f dash of x. F dash of x is equal to 6x square minus 30x plus 36. Taking 6 outside, and we get it as 6 into x minus 3 into x minus 2. Now, when f dash of x is equal to 0, we get x is equal to 3 and x is equal to 2. Now, these are the critical points. Now, evaluate the value of f at these points and also at the end points, that is, for values of x is equal to 1, 2, 3 and 5. Let's see. Now, f of 1, we substitute the value and we got it as 24. F of 2, we got it as 29. And what is f of 3? F of 3, by giving the value x is equal to 3, we get it as 28. And f of 5, on giving 5, substituting and solving, we get it as 56. Now, from this, we can conclude that the absolute maximum value is, out of this, maximum value is 56. So, absolute maximum value is 56 at x is equal to 5. And the absolute minimum value is 24 at x is equal to 1. Right? Now, let's have a look on the difference between local maxima minima and global maxima minima through the graph. As you can see, the local maxima at 3 points, and these are the local maxima. Okay, as you can see here, And have you noticed the global maxima and global minima? And this peak corresponds to the global maxima. And the lowest point in the graph will give you the global minima. Now, from graph it is observed that a function can have multiple maxima and multiple minima. And the point where the function take minimum value is called the global minima, and the other minimum points are called local minima. And at all minimum points, the first order derivative will be 0. Then the point where the function take maximum value is called the global maxima, and the other maximum points are called local maxima. So far, we have discussed all theoretical concepts related to maxima and minima. Also, we looked into some problems based on this. Alright? Now, if we think at the application level, is it possible to find the company's profit using maxima and minima concepts? Think. And now, with the knowledge gained, let's move on to the summary section.
Manorama Horizon. Learning made simple.